Welcome to CW 3.6. Today we're going to be working a lot with your calculator. So go ahead and pause the video and grab your calculator if you don't have it already. So we're going to start with number 1 right here. We have 4 examples to talk about. It says you're choosing between 2 texting plans. Plan A is a monthly fee of $20 and a charge of 0.05 or 5 cents per text. Plan B has a monthly fee of $5 with a charge of 10 cents per text. So kind of an old problem. Phone companies don't really work this way anymore, but they used to work this way about 10 years ago. So that's kind of the context of this question. Essentially, it's saying per text you send, you have to pay money. So for plan A, let's do letter A right here. Let's say f of x, because it says f. It says express a monthly cost. So f of x is going to be our cost. And x is going to be the number of messages sent. So it says 0.05 per text, so 0.05x should be how much it costs per text, and adds a monthly fee of 20. That's like your one-time fee. So for B, we'll do the same thing. The monthly fee this time is 5, so we'll just put 5, and then a 10 cents per text, so 0.10x. So I know it says monthly, but don't worry about that, because it's basically saying how much we'd pay in a month anyway. So let's go to part C now. We have our 2 equations. It says, for how many text messages will the cost for the 2 plans be the same? So if we're looking for when the cost will be the same, you simply make the equations equal. So think of it as like we want f of x to equal g of x. So of course we could just solve it algebraically, but I want you to use your calculator. So let's grab our calculator. We're going to go to apps, function. Let's actually type it in. 20 plus 0.05x, 5 plus 0.10x. We graph it. Got to do a little bit of zooming out here. Okay, so right there we kind of see it happen. That's the graph we want right there. So I'm just going to go back to my chart or my problem. One going like this, other going like this. The intersection, to find that, all you do is you tap near it, menu, function, intersection, and just hit OK. So 300, 35 is that point. So we got to interpret that. That would mean at 300 texts, both plans cost $35. And that's part C. Now let's go to the next one. A machine produces open boxes using square sheets of metal measuring 12 inches on each side. The machine cuts equal-sized squares from each corner. Then it shapes the metal into an open box. So to do this, you got to kind of visualize. So here's a square sheet. And imagine you're cutting out these corners like this. Now the corners are all uniform. And it tells you that because this is equal-sized squares. And then that's going to lead to some shape like this. Okay, so we're trying to get it to look like that. That's our goal. So now it says express the volume as a function of the length of the side of the square cut from each corner. So let's call the corners x. And if the sheets are 12 by 12, that would make the remaining part 12 minus 2x. 12 minus 2x. And if we fold it, that would mean these are all 12 minus 2x, and the height should be x. So there's a visualization. So for the volume, recall the volume of a box is simply length times width times height. So this should be x times 12 minus 2x squared. Now let's find the domain and find the max volume. So for this, let's use our calculator here. So we're going to go back to it. From here, we're going to type it in. X times 12 minus 2x squared. If that happens to you, I think you got to put a times right there. Yeah, if you get an error, just put a times in front of it. And graph. Now notice my graph's pretty funky. That's happening because my scale is so severe. So to reset it, we're going to go shift plot and then shift escape. And now it's a little better. So I'm going to zoom a little bit so I can kind of see a better graph here. Okay, this looks better. Okay, so I'm going to do a quick sketch of that on my paper. So of course, if I ask you for the domain of this graph, you'd say everything. But for a word problem, I can see that I actually only want this part from here to here. And that's because this particular piece right here, this can't be negative. So it wouldn't make sense to make that piece negative. So if I go back to my calculator, if I find the root right there, the root is 6, 0. And I can see the other one is going to be 0, 0, which means the domain should be 0 to 6. Because if you imagine you're the one cutting these corners, we can't make this corner bigger than 6 because then that would exceed 12 on both sides. So that's not too bad. Now if our domain is just this part, that means we can find the max by simply finding the extremum right there. So let's go back to the graph. Function extremum, 2, 128. So that point right there is 2, 128, which means the max volume, or the max volume, equals 128 inches cubed. And that happens when x is equal to 2 inches. Okay, so there's our first two. We're on our last two examples here. Now it says we have fencing to enclose a rectangular garden. So if you imagine a rectangular garden here, here's our width, here's our length, width and length. We can see our perimeter is going to be 2L plus 2W. So 140 should equal 2L plus 2W. 70 is equal to L plus W. So W should equal 70 minus L. Now the reason I did that is because we're trying to find the max area, and the area is going to be length times width. And now that I have this expression for the width, look at what I can do here. I can plug it in. Area is equal to L times 70 minus L. So this formula right here generates the possible area given these parameters. That here's my box I'm working with, and the fencing is 140. So that's my play to work with. So we're going to graph that using our calculator, and we're going to find the max area. So let's go back to it. We're going to type in x times 70 minus x. Let's play with our calculator a little bit so we can see it. Okay, right there. And I'm going to do extremum. So I have 35, 1,225. With something like this. Now we interpret it. That would mean the max area is 1,225 yards squared, and that happens when the length is 35 and the width is 35. And I got that because the length right here, that's our x value here. And if it's 35, I plugged it in right here, and you can see the width should also be 35 because of this fact, or this fact right here. We know that they have to add to 70. Okay, so I'm going to highlight that. I'll go to our last question. Now for this question, it says, figure 1.84 shows that the point, this thing, is a point on the graph of this parabola. Express the distance from P to the origin as a function of the point's x-coordinate. So essentially, we're trying to express this length, d, as a function of the x-coordinate. So the first thing you want to do is cross out the xy. We're going to write x, 1 minus x squared. That's kind of profound because if the parabola is y equals 1 minus x squared, you don't want to actually write it as xy because that's not helpful. What you want to do is rewrite this y part as an actual function in terms of x, because now we have this nice point. And for distance, we just need 2 points. We have the origin, which was told to us right here, and the point x comma 1 minus x squared. So recall the distance formula. This is from your algebra class. The distance formula is x2 minus x1 squared plus y2 minus y1 squared. So we're going to plug it in. That would be x minus 0 squared plus 1 minus x squared minus 0 squared. Let's do some algebra. X squared, and this would be 1 minus 2x squared plus x to the 4th. Go a little bit further. X to the 4th minus x squared plus 1. So what we have here is a formula that will generate how far we are on any given point on the parabola, so anywhere, to the origin. So for example, if I plug in 1, this formula will generate the length of this line. If I plug in 2, the formula will generate the length of this line. So that's pretty cool. So the extension is going to be find the minimum distance to the origin. So to do that, we're going to use our calculator. So we go back to it. Let's put the square root of x to the 4th minus x squared plus 1. And we got to get a better picture, so let's standardize it again. There we go. So now I can kind of see more clearly here. There's our graph. And notice how we actually can calculate the extremum because there's a minimum point right there. 0.707, 107, 0.866. And actually, if we go to the other side, notice how it's actually the exact same thing, just negative. So that's pretty cool. So I'm going to go back to my drawing here. I'll sketch what we saw. Something like this. And the minimum points, I'll put an arrow here, were plus or minus 0.707, 0.866. So if you imagine the graph, the minimum distance should be somewhere over here, and that length is 0.866. That's pretty cool. So there's our minimum distance. It's going to occur at x equals plus or minus 0.707.